On October 5, 2025, the world changed. A NASA physicist stood on stage and calmly announced that her team had created something once thought impossible, a prototype engine capable of reaching 0.9 times the speed of light. Dubbed Photon Arrow, it doesn't burn fuel, it bends physics. It doesn't launch, it glides through space powered by laser arrays and mass-dampening fields. If true, it means we could reach the nearest star in under 5 years. But this isn't just about speed, it's about everything that happens next. New worlds, new questions, and a future that starts now. On October 5, 2025, NASA held a live press event in Pasadena, where senior physicist Dr. Emily Chen announced a startling breakthrough, a prototype propulsion system that could approach 0.9 C or 90% the speed of light. The project, internally known as Photon Arrow, is the result of 6 years of classified research funded under DARPA and NASA's Breakthrough Propulsion Physics Initiative. The craft itself, still in prototype form, was built to test an exotic propulsion model that doesn't rely on traditional fuel. According to Dr. Chen, the craft's inertial mass is reduced using a high-frequency electromagnetic field, allowing rapid acceleration. In early August 2025, a scaled version was tested in a vacuum chamber, showing acceleration patterns previously only modeled in simulation. The scientific community reacted with cautious amazement. NASA's fastest prior probe, the Parker Solar Probe, reached 700,000 km/h, just 0.06% of light speed. If Chen's prototype proved scalable, it would shatter every spaceflight speed record. Officials from ESA and CNSA called for collaborative oversight and independent verification. Despite the media frenzy, NASA clarified, the craft won't carry humans or even large payloads for decades. A full-scale unmanned mission might launch in 2028, with interstellar reach possible by 2035. But one fact is undeniable. A NASA scientist has publicly stated they have engineered the world's first near-light-speed vehicle. The next challenge isn't publicity, it's physics. Lightspeed is not just fast. It's a cosmic wall defined as 299,792,158 ms. It forms the ceiling of motion in Einstein's 1905 special relativity. As objects approach this speed, their mass increases asymptotically, requiring infinite energy to continue accelerating. Photon Arrow claims to bypass this wall using what it calls a mass-dampening field. This experimental technology reduces the spacecraft's effective inertia without breaking conservation laws. In tests conducted between March and July 2025, a small-scale vehicle was accelerated to 0.66 C over 12 minutes using external lasers and onboard field generators. The energy required remains immense. Dr. Chen estimates that to push a 1-kilogram payload to 0.9 C, it would take 5.2 x 10^18 joules, roughly the total US energy output in 1 year. Yet the craft doesn't carry this energy as fuel. Instead, it receives directed energy beamed from orbital stations, reducing onboard mass and allowing more efficient acceleration. However, problems remain. Collisions with even micron-sized dust particles at such speeds release enough energy to vaporize metal. A new kind of electromagnetic deflector shield is in development, according to an internal NASA brief dated August 9, 2025. Until that's resolved, even unmanned flights remain risky. Even if the physics hold, building a ship to survive such speed is another story. Photon Arrow isn't just theoretical. It's a working prototype built over 32 months in collaboration with Lockheed Martin Skunk Works and the MIT Plasma Science Lab. The craft is made from ultra-light, temperature-resistant alloys fused with graphene composites. At its core is a superconducting ring operating at 4 Kelvin, stabilizing the mass-dampening field. The external shell features multi-layered shielding designed to absorb impacts from cosmic particles moving at relativistic speeds. At 0.9 C, a grain of sand hits with the force of a grenade. To survive, Photon Arrow's outer plating disperses kinetic energy through nested plasma barriers. Test shielding held up during simulated collisions at 0.75 C using particle accelerators in July 2025. Propulsion is driven by phased laser arrays, stationed in high Earth orbit, beaming coherent light into a rear absorption panel. This energy accelerates the craft without the burden of onboard fuel. These lasers, each rated at 15 petawatts, are powered by orbital solar farms launched in 2023 and fully operational by 2024. Thermal control is equally critical. As the craft moves through space, it absorbs ambient radiation and heat. A system of radiative cooling panels unfolds once in vacuum, operating between 220 degrees Celsius and 160 degrees Celsius. Engineers call this dynamic thermal skin, a concept first drafted in 2019, but now fully implemented. The first scaled test of Photon Arrow occurred on August 17, 2025, in a deep vacuum test chamber at the NASA Glenn Research Center. The model, just 1.8 meters long, reached 0.58 C in under 14 minutes, with acceleration confirmed by 3 independent sensors positioned along the chamber's magnetic track. Key telemetry data included inertial mass fluctuations, thermal gradients, and Doppler-shifted beam reflections. A surprise finding emerged on test cycle 9. The craft momentarily maintained velocity stability at 0.62 C with a flat energy curve. This hinted at an unexplained field equilibrium point, now dubbed the Chen horizon by the research team. On Sunday, September 4, 2025, results were submitted to Nature Physics and reviewed by a joint team from Caltech, CERN, and JAXA. While impressed, reviewers requested longer duration trials in open space environments. Dr. Chen confirmed a suborbital demonstration would launch from Vandenberg Space Force Base in January 2026 using a full-scale model and orbital laser support. Despite initial skepticism, the broader scientific community began to pivot. By October 20th, the International Astronomical Federation convened a special panel to discuss the implications of a verified 0.9 C capable propulsion system. The conversation had moved from theoretical physics to policy, regulation, and engineering readiness. With growing confidence in its performance, the world now asks, what will we do with this craft? NASA's first target is Proxima Centauri b, located 4.24 light-years from Earth. Under current technology, that journey would take over 70,000 years. With Photon Arrow reaching 0.9 C, a probe could arrive in just 4.8 years. A proposed mission, Arrow 1, aims to launch in 2030. The uncrewed craft would carry ultra-miniaturized sensors, imaging systems, and a quantum-linked communication node. Data would return to Earth via quantum entanglement relays, a technology still in experimental phases as of October 2025. Longer-term plans involve sending a swarm of microcraft, each under 10 kilograms, to explore multiple exoplanets. These probes would act autonomously, relaying data back in bursts. A mission to the TRAPPIST-1 system, located 39.6 light-years away, is tentatively slated for study by 2040. However, there are geopolitical concerns. On October 12th, the UN Office for Outer Space Affairs issued a statement calling for international oversight on interstellar propulsion, citing fears over militarization and sovereignty in deep space. Both China and India have expressed intent to pursue similar technologies, and the European Union is planning a joint propulsion lab by 2026. What was once science fiction, traveling between stars within a lifetime, is now strategic reality. The world must balance ambition with responsibility. NASA's roadmap for Photon Arrow began quietly in 2019 with DARPA funding. Now, as of late 2025, it's transitioning into the public and operational phase. Key milestones are set through 2040. In January 2026, a full-scale prototype will launch into low Earth orbit for autonomous field testing. By 2027, this model will conduct acceleration trials in space, attempting 0.7 C over a 6-hour trajectory using orbital lasers and deep space tracking. The proposed interstellar mission, Arrow 1, is scheduled for construction beginning in 2028, with final assembly at NASA's Lunar Gateway Station. It will launch by 2030, arriving at Proxima Centauri by 2035.